Professor Harrit has published more than 60 collaborative peer-reviewed articles in the most prominent scientific journals in his field. His current non-9/11 focused research field is in time-resolved structural investigation of transient intermediates in chemical reactions on timescales of 1/millionth of a second by X-ray scattering. That sounds pretty exciting. That might even compete with the kind of thing that Jonathan Cole does in his backyard. I'm not sure. But it might all happen much more quickly than the human eye could take in. Professor Harrit is also the author of a recent study, Active Thermitic Material Discovered in Dust from the World Trade Center Catastrophe, that has evoked lively interest around the world and has led to invitations to him to speak in many countries. He has made prominent media appearances in Europe. I think it's one of the signs of the degree to which there is a kind of media blackout on discussion of research relating to the events of September 11, 2001, is it complete exclusion from mainstream media on this continent?
Not quite.
Not quite,
It's
but
breaking.
very.
It's breaking.
It's starting to change, and I'm confident that it will continue to change. He has, I think, important new research to present to us today. Professor Harrit's testimony this afternoon will be on the subject of thermitic material found in the World Trade Center dust. Kindly welcome him.
Thank you very much for this kind introduction and for inviting me, and for all the friends we have here in Canada, and for our hosts taking so generously care of us. Today, in my presentation, we will zoom in on the dust, which we have all seen several times in the presentations preceding this one. And in such huge quantities in what was called pyroclastic clouds. And the pyroclastic cloud is a dust cloud which is hot. And the temperature of these clouds was emphasized by Kevin Ryan in the preceding presentation. There was plenty of dust. And it influenced so many people in New York City. One of them being a woman who was living on the corner of Cedar Street and Liberty Street. Is this corner here. Her name was Janet McKinley. Would it be okay if I take this one off? Thanks. Thank you. Her name was Janet McKinley. And she lived at the corner of Liberty Street and Cedar Street on the 4th floor. She actually had a view of the plaza. And when the South Tower came down, she hurried away very cleverly because the dust coming out was not very healthy. She wrapped a wet towel around her head. And she was allowed to come back to her apartment about a week later. And this is what it looked like. There was a thick layer of dust all over, and she had a cleaning job to do. She already very early saw the magnitude of the event and developed kind of a spiritual relationship with this dust. So she kept some of it for the purpose eventually of making it into a piece of art, because she also had an artistic mind. And this is a snapshot from the day when she's coming in. Some details. And this is such an example of what such an artwork could look like from Janet. I like it because you see the dust here in this glass vessel. The light is shining onto it, and this is what we're going to do today. And hopefully something green will grow out of it and bring us some hope. Thank you. On the background of the reports from the J.R. Lee Group, and the United States Geological Survey, which Richard Gage was telling us about. This dust actually ended up from Janet McKinley's apartment in Utah with the gentleman who we see here receiving, this is not Janet McKinley's dust sample, he's receiving another dust sample. And at this point, I have to ask our chairman for the permission to call for an applause in a little moment. Because this gentleman here is the man who actually initiated and carried out most of the research I'm going to present here today. And he should have been here, but circumstances prevented that. He is hopefully eventually watching, and so we may send him a greeting in a little moment. He is a genuine experimentalist, a great scientist, and a great human being. So please join me in sending our greetings to Stephen Earl Jones. And we see here Professor Jones taking this sample and treating it the way that Kevin just described. We put this dust into a plastic bag and apply a magnet onto it. I'll show you in a little while, and you'll get the opportunity yourself to do this. But on another sample, because this emerged quite recently from New York City, a big jar, 5 gallons of dust. And this is the biggest actually sample of dust I've ever seen. I haven't seen this one. But last morning, I got a sample from this jar, and it is here. And it's huge. This is a lot relatively to what we used to get of samples from people. So I have not, I have taken actually a small sample out of this bag, put it into a smaller bag here, and I also brought a little magnet here. And I will give you all an opportunity to play around with it. I have to put down the microphone, and I have to yell eventually. Or you can hold it. Okay, yes, please.
I can hold it. Thank you.
We'll bring it first. What you shall do when I bring this to the panel members, you should take the bag horizontally, or you can also put it vertically, and then apply the magnet to the dust, and you'll see something coming along. Play a little with it. The challenge for you is to isolate a black line of particles following the curvature of the magnet. The magnetic field is strongest at the edges. So try to pull out some magnetic material from the bulk and eventually isolate what probably will be a black line of small particles. And this, what I'll tell you in a little while what this would be. Two words of caution. Please don't open the plastic bag. This is one. Next, don't let this magnet get too close to your Rolex. Chances are you'll never get it off again. And cell phones, etc. So be careful, and we can have it working all around. You're all welcome to try this.
Professor Lee is commenting on the power of the magnet at the moment, if you can't hear from the other side of the room.
Thank you. This picture has also been shown by Kevin Ryan, and this is some of the stuff you can isolate from the dust by means of the magnet. This is the raw dust. And most of it, what you'll see here, the black stuff, are these iron spheres which have already been mentioned several times so far. With a little bit of luck, you may also get a chance to see, I don't know about this sample, I just got it yesterday morning, I don't know how much is in it, but these red, we call them chips, is what we're gonna talk about for the next 20 minutes or half hour. It was first presented to the world in 2007 on December 15th in Boston by Stephen E. Jones. And so this is a close-up of one of these chips. We call them red-gray chips for the obvious reason. It's red on one side and it's gray on the other side. We see the red side here. This one is one of the biggies. It's a real huge one. It's about 2 millimeters from one end to the other. Most of them are smaller. You will need a microscope actually to detect them, or a very, very strong magnifying lens. Following this publication of Stephen E. Jones, I was asked to join this team of scientists investigating these red-gray chips, and the work eventually ended up in a publication on April 3rd of 2009, and this is the content of this paper, which I will present to you for the next half hour or so. The paper is based on 4 samples, which Kevin already mentioned in the previous presentation. Janet McKinley's sample is on the corner of the World Trade Center Square Plaza, and the other one here is from the Brooklyn Bridge. Sample number 3 and sample number 4 is a little north of that. In all 4 samples, we found these red-gray chips. These are the 4 samples, A, B, C, and D. And you'll see the magnifying bars here. This is 1/10 of a millimeter. This is a big one, 1 millimeter. Actually, yeah, it is huge. The other ones are more normal. This is a side view. You see the red face and you see the gray face. It will be the red face which will be interesting around here. This is an electron microscope of a chip, and on electron microscope pictures, there are no colors. I just show it to give the dimensions of the chip. This is 1/10 of a millimeter, so this is the thickness. This is the red layer, and the gray layer is here on the top. Further characterization, the first part, what we are doing now is we are describing the chips. This is a picture of a 3 different microscopic representations of this magnetic extract from the dust. This is an ordinary optical microscope picture. This is what you see with your eyes. And these are 2 different kinds of electron microscope called SEM, scanning electron microscope pictures, obtained in 2 different ways, which is not maybe so crucial in this connection. But here, the white parts represents actually the red parts here. And this picture in particular, based on backscattered electrons, reflects the weight of the atoms being observed. And it is a bit darker here, means apparently, and this is our first cue, that the red face is composed of atoms which has a lower atomic weight. I will be careful not to carry the science, aspect too far, but I have to use some technical terms. We are also using another technology called energy dispersive spectroscopy, which Kevin already has mentioned. The trick is here that you direct an electron beam like the laser beam here on a specific spot. And this we can do with an accuracy better than 1/10,000th of a millimeter. We can hit a specific spot with an electron beam, and the material responds by sending out X-rays. And these X-rays you can analyze into a spectrum, and from that spectrum you get specific information of which elements are present in the spot you hit with the electron beam. And these so-called energy dispersive spectroscopy results from the 4 samples already here showing us. I'll pick the lowest one. They look small but this is because the carbon peak is so big. Carbon is C, O for oxygen, Fe for iron, Al for aluminum, Si for silicon, and these are 2 other iron peaks. Look at the lower one. I've already mentioned now, and these are the elements, and here there's nothing else in the red phase, the red layer. Iron, silicon, aluminum, oxygen, and carbon. Very simple composition, actually. This is an even greater magnification, also an electron microscope picture of the red phase, where we further can identify the particles involved here. We see some plate-like structures here. We see some smaller, but still crystalline, meaning that they are hard. And apparently some, what would you say, random phase here. And this is, I can already now say, this is the polymer, this is the plastic. Because this material has the properties, it has the properties common with paint. Meaning that these particles here are embedded in a plastic matrix. I use the word plastic to make it simpler for you. A scientist would say a polymer matrix, but maybe that is too far out. You see here the magnification here is 50,000. This is 1 micrometer. This is 1/1000th of a millimeter. Further information we get if we are applying this energy dispersive spectroscopy to such a cutout of the a close-up of the red phase. This is an electron microscope. This picture shows where the iron is. This picture shows where the aluminum is, and where the oxygen is, where the silicon is, and where the carbon is. And there is some correlation. You can, for instance, see here that the aluminum is found in the same regions as the silicon, and we may already now get the impression or the idea, the information, that the aluminum and the silicon is located in these flat, what should we call, flakes, which is seen here from the side, actually, while the iron and the oxide is located here in these small particles. And that is what it is. I can tell you already now. This white particle here are iron oxide. Now, one very important point here is the aluminum bound to the silicon or isn't it? Because aluminum and silicon are very, very common elements in nature. It's so that the most common element on Earth is oxygen, number 2 is silicon, number 3 is aluminum, because they're omnipresent in stone, granite. But we did an experiment where we dropped 1 chip at a time into an organic solvent called methyl ethyl ketone. This, ladies, is almost the same as acetone, which you all know for removing of your nail polish, right? So let's say it's acetone. It would work the same thing, but we use methyl ethyl ketone because it has a higher boiling point. It's easier to work with. Now, if you drop one of these chips into methyl ethyl ketone, the red phase swells like a sponge. Like if you put a dry sponge in water, it swells almost 6 times. And this is what you see here from the side of the red layer. This is an electron microscope's picture of the swollen chip. And now we're applying the same technology. We are trying to map the chip according to elements. And the information you get here is that the aluminum distribution is now different from the silicon distribution, meaning that they cannot be bound together in a chemical substance. If they were, they would not be separated. Furthermore, if we apply this energy dispersive spectroscopy to a silicon-rich area like this one, we get a spectrum out like this, only silicon. Here, a little iron oxide, because you cannot expect it to be completely, of course you see a little iron also. And if you apply it in an area where there's only aluminum, like here, you see aluminum and very little silicon. This means that the silicon and the aluminum are separate entities, and the aluminum can move around as a consequence of the swelling with the methyl ethyl ketone. This is an indirect but a good proof of that we have the presence of elemental aluminum, which is very, very important. But it is not the strongest evidence we have. The strongest evidence we have comes from the reactivity of these chips. Just a second. That's better here. Because when you heat these chips up, they react. It's not easy to show, what we're aiming at now is, you should know, we are talking about nanothermite, we're talking about the thermite reaction. You have seen this reaction scheme many times already. You've seen, and it was invented, thermite is a very old thing. It was invented by Hans Goldschmidt, a German chemist, in 1893. It was patented in 1898 and applied for the first time in 1899 for welding of tram rails in Essen in Germany, in the Ruhr area. Because in the thermite reaction, as you have already heard many times, you form elemental iron at a very high temperature. So it's very useful for welding. Now, but it can also be used to destruct things, which we have seen Jonathan Cole demonstrating so nicely. And this is the reaction which you would expect. Notice that we have seen there is in the red grade chips, there are iron oxide. We have seen this from the energy dispersive spectroscopy, and we have a good reason to expect elemental aluminum to be present. So wonder what happens when you heat them up. This experiment it's a little difficult to demonstrate because they are so small. So you have to believe me that the experimentalist here is applying a microtorch, and to the left of the flame there is a tiny chip. It's moving the flame from right to left. And what happens when he reaches the chip is, you can see those sitting close here, you can see a yellow flame sticking out. In this experiment, actually, he could feel something was hitting his hand, but he could not find the particle afterwards. This we have found on many other occasions. And this is not showing that it could take off like this is not very scientific. What you should do is you should put them into an instrument. But first, let us compare a chip which Kevin Ryan found in the dust. And this was lucky find in the sense that it, in this case, you can see both, it's a semi-reacted chip. You can see both that there are some remains of the red phase, and there are these iron spheres which have been described so much. This is a residue from the flame test. It's not perfect because it cools so fast, but we think that there is a pretty good resemblance between this chip which has been ignited in the laboratory and this chip which has been found in the World Trade Center dust. Oh, I can operate this. These are to certify that it really is an iron-rich sphere being formed in the flame test I just showed you. This is the same chip. We are applying energy dispersive spectroscopy on a point like here. You see iron, a little calcium, silicon, aluminum, and an iron spot here. This is an iron-rich sphere from the dust. And again, you have the same fingerprint. You see iron. You also see calcium together here with sulfur. This is a contamination of wallboard, calcium sulfate on the surface. But most importantly, the predominant peaks here are iron, silicon, aluminum, so they really do resemble each other. Okay, come on. Now it can stalls. What's happening? Okay. But it's to apply a microtorch is a nice demonstration. It's not real scientific. But if you want to have a quantitative measure of the heat developed in this reaction, you put it into an instrument called a differential scaling calorimeter, which is a device where you heat up the item, the little chip, and you measure the flux of heat going in and out of the sample. And here, this is the blue line here. So we are heating it up in degrees Celsius, and we're heating it up, and suddenly here at around 430 degrees, it goes boom. It goes simply off the roof, and the needle bends, and you have a very sharp, very narrow spike energy being released, indicating a chemical reaction. The red line here is the only published differential scanning calorimeter measurement of nanothermite. So this is the only comparison we have. And actually, the one we got out of World Trade Center is better in terms of its narrow. I'll return to this energy this energy formation here because we have in watts per gram. This is energy per gram. I'll return to this. This picture also was shown by Kevin Ryan, and these are the various residues. These are chips which all have been into the DSC machine. We are taking them out, and we are observing these reaction products, the metal spheres. And these pictures, also shown by Kevin Ryan, is what the chips look like when Kevin is preparing the nanothermite in his backyard, and we see the same red chips here. So what else? So we believe that we have found what we call nanothermite. Let me repeat. You have a plastic matrix, and in it you have very finely dispersed aluminum and iron oxide, and that's it. The methods of preparation has already been described by Kevin Ryan, but now I'll meet one objection which has been met over the last 2 years, that this is just ordinary paint. And no, it isn't, I can say, because the primer paint applied on World Trade Center, as you see it here, this is what you do to steel when you apply paint on it immediately for anti-corrosion purposes. But the primer paint is also red because it does indeed contain also iron oxide, which is red. This is a sample from the NIST report, very specifically isolated. You see the primer paint, and from the towers. But the same report also contains a description, a chemical description of what the composition of the primer paint is. Now I have to be a little technical. This is from the NIST report. And besides, these are all the liquids. You don't have to worry about that. But the hard stuff in there is iron oxide. It is yellow. And then it's a compound called zinc yellow, which to the trained scientist, we know its true name is zinc chromate. And it is indeed lemon yellow. So if you, and this of course are percentages from the wet paint. The only thing here which is not immediately understandable is what the dynamic pigment, but what this 33% is, you can find if you go into material safety data sheet of the dynamic paint, and you can find out these are very small compound content of zinc, iron oxide, fume. You do a little calculation, and you find out it's very easy that the content of zinc chromate in the dry paint is about 1/3. Now the point here is we do not see zinc. We do not see it. I go back to a picture I showed you a couple of minutes ago of the energy dispersive spectroscopy from the red layer here. And here we have blown up the area where you should expect chromium. You can see a little chromium here. We just cannot see zinc. And when you blow up the vertical scale, of course, all the, what you call it, the regular peaks, they go completely out off the roof. So the signal from chromium is the level of the noise. It means there's nothing in there. And we can't even see zinc. So conclusion here is that the red-grade chips cannot be the primer paint because we do not see zinc chromate. Now then, maybe somebody who has went into our paper, I'm just telling the experience that we have had with the debunkers. And they fell down on one of the pictures in the paper here, which shows the chip which was used for the swelling experiment with methyl ethyl ketone. I say, ha! You see here you have chromium and here you have zinc. That is proof that it's a primer paint. The point here is that the previous picture, these EDSs have been taken on chips which have been broken, so you have a clean surface, which is the way to do it. Now, in the experiment where we had to put the chip into methyl ethyl ketone, we could not break it, of course. So this is actually, it shows all the contamination from the rest of the building. Let me just point out here, you see a great big sulfur peak, and you see calcium is big. We've already talked about wallboard. This is contamination of calcium sulfate from the wallboard, which was all over. And this zinc chromate could very well be primer paint, sticking on the outside of the red grade chips. And the point is, when you break the chip, where you get a clean cut, there is no zinc chromate. That is one reason that the red grade chips is not the primer paint. Another one argument depends on the thermal stability of the primer paint, because already you may think, why should somebody paint World Trade Center with a paint which reacts violently at 430 degrees centigrade? Yes, that is true. And even in the NIST report, they used the thermal stability, or you may say reactivity, of the primer paint as a measure for the temperatures for which the steel beams have been exposed. They took actually a steel beam, put it into an oven, and saw what happened to the primer paint upon heating. And if you keep the beam at 250 degrees centigrade, it starts cracking. And it's called mud cracks because it looks like what an African flood looks like in their summertime. If you heat it further to 650 degrees centigrade, the mud cracking becomes severe. And beyond that temperature, what happens is that your scales are being formed, which this is because the organic binder actually starts charring. There's no organic compounds which are stable, basically, beyond 450 degrees centigrade. But this is, so it is being converted to carbon, and it starts peeling off. And this experiment you can carry on until 800, 900 degrees. I've done it myself. But these are pictures from the NIST report. So from looking at the mud cracking of the paint, they could tell how hot the steel beams had been. And I can tell you as a footnote that they did not find any steel beams who had been beyond 250 degrees Celsius based on this ways of measuring. Okay, but what we are aiming at here is that what we found takes off at 430 degrees centigrade, but the primer paint is thermally stable. So that's why the red grade chips are not primer paint. No. Now, where do the red grade chips fit into the collapse scenario? Until I saw one of David Chandler's videos, I was very reluctant going into hypothetical blast scenarios. And I think already during previous presentations, we have gone too far. But I'll do it nevertheless now. But before that, let me try to straighten out a little bit about the concepts of explosives. What is explosives? What are incendiaries, etc. Because an explosive must act by means of force. It is a chemical reaction where a gas is evolved and you knocked things over like that with the pressure, with the force. And in order to do that, it has to be very fast. Now, I have put a question mark here after energetic materials in the headline. The point is that explosives are not particularly energetic. Many people think that. But the fact is you get much more energy out of burning, say, 1 pound of coal than you get from firing 1 pound of TNT. But how long time does it take you to burn 1 pound of coal? It takes some time. But if you ignite TNT, it goes very fast. So the characteristic of explosives are not that they're energetic, but they're fast. They deliver their energy in forms of gas pressure very, very fast. Another thing which I will bring up, which is new to these proceedings, is that among energetic materials you also find rocket fuel, or a more precise term would be a propellant. These are also materials which are giving off gases, but they're doing so slower than explosives. Obviously, you can use it in rockets, and they burn from the surface, in contrast to explosives, which burns with the whole bulk. And another thing which is an incendiaries thermite and incendiaries thermate also belongs to this family, but thermite and thermate acts by means of heat, contrast to explosives which acts by means of pressure. And relative, even though we saw Jonathan Cole demonstrating these wonderful experiments in his neighbor's garden, they are still slow on the time scale of explosives. Explosives are very, very fast. Some of the explosives, actually the combustion zones move more than 20 times the speed of sound. TDX, for example. Maybe some of you have heard that. Then we have to consider and take the difference between what people call conventional explosives and what I would call composite explosives, because there's a lot of discussion going on in the community and beyond. Are nanothermite an explosive? Is it a high explosive? Is it a low explosive? And is it an incendiary? So I just want to straighten out these concepts at your service. A conventional, what people call conventional explosives, I would rather call a molecular explosives. But while a composite explosive, there the reactants are present as different powders. Gunpowder is a composite explosive. It is composed of pulverized carbon, pulverized sulfur, and pulverized saltpeter. And this mixture actually was invented by the Chinese in the 10th century, about that. But conventional explosives like TNT are molecules. Were explosives used in the demolition of World Trade Center? Obviously. I mean, this has been made quite clear previously. Let me just, I could deliver a 20 minutes, 30 minutes actually presentation on nanothermite and why nanomaterials are better and how they work relative to molecular materials. Just very shortly. This is TNT, a very common explosive, trinitrotoluene. And this is RDX. It's called cyclotrimethylene trinitramine. And the reason why explosives are so fast is that the electrons only have a very short range to go. Both parts of the reaction are actually in the same molecule. So in TNT, the electrons only have to move from here and out to the nitrogen group. This is a distance less than 1/10 or 1/1000th of a meter. While in gunpowder, which is a mixture of powders, the electrons have to move from one particle to the other. Fireworks, rocket fuels, and old-time thermites. Hans Goldschmidt's thermite is also a composite material. He just grounded aluminum and iron oxide and mixed the two powders. Very slow, because the electron has to move so fast. Now the point is, in nanotechnology, you start with composite materials, but you make the particles smaller and smaller and smaller. And this is what happens to a thermite reaction. As you make the particles smaller, the time of reaction gets shorter and shorter, and then of course you deliver the energy in a much shorter time, meaning that the effect gets much higher, and eventually you approach the delivery rate to that of molecular materials. The advantage of thermitic materials is that the energy content per volume is much, much higher than the unconventional materials, meaning that you can pack much more energy into a smaller volume than you can do with dynamite or TNT or RDX. Now, okay, so the one problem which comes up, are there such a thing as thermitic explosives? And we cannot point to something you could go down and buy in the local store. But we can point at some reports, because even these people, they have to apply for funding, and they can't refrain from bragging and telling about their research. So these are just two quotes here from a symposium in San Diego in 2001, where I quote Dr. Anje Mitiolek. At this point in time, all of the military services and some Department of Energy and academic laboratories have active research and development programs aimed at exploiting the unique properties of nanomaterials that have potential to be used in energetic formulations from advanced explosives and propellant applications. Okay. Another thing is, which I used to quote here, is a report from MIT, actually, Technology Review, where John Gardner describes the new nanotech explosives as smaller, cheaper, and nastier. And these are the guiding principles behind the military's latest bombs. The secret ingredient, nanotechnology that makes for a bigger boom. The military is also trying to make sure that its bullets kill quickly. Quote, getting the government to change the way they kill people is difficult. He's complaining that he doesn't got sufficient funding for developing nanothermitic explosives. But the fact is, regarding World Trade Center, we do not know the nature of the explosives being used. Let me stress that. Obviously, we see the result of explosives. We do not know actually if they were based on thermitic materials or molecular materials, which somebody called conventional. We are still waiting for this to be elucidated. The rocket fuel, the same thing goes for there. They exist as thermitic. Actually, the second step in the Challenger, three-step Challenger rocket, which brings up the space shuttle, is nanothermite. It's aluminum powder and ammonium nitrate. So it is a genuine nanothermite, the second step. So you have rocket fuel which can develop pressure, can do pressure work relatively slowly, which is what a propellant do. I'll return to this in a little while. Obviously, incendiaries which act by means of heat, they must by necessity be thermitic. And this is what we observed, molten iron in the rubble, molten iron coming out of the South Tower, and these iron spheres being formed unambitiously indicating that thermite must have been there one way or the other. And if you do a little calculations on the findings of the RJ-Lee group of the iron spheres in the dust, you'll realize that there must have been more than one source of these iron spheres. No single source can account for the amount of iron spheres detected by the RJ-Lee group. Now I will show you a video which David Chandler did not show. And I must admit that up until this point, I did not, as I said, indulge in hypothetical blast scenario. I wouldn't speculate where the red grade chips fit into any blast scenario. But upon watching this one, I changed my mind. And there's some spin-offs actually of this, because this is unrelated to my talk, but you'll see here how the explosives actually are occurring above the impact point of the airliner. Now, the pile driver model and the pancaking model died. And you'll see in a while, you'll understand. But what we are aiming at here is the fragments which is coming out of the towers. I'll play it through, and then I'll go back and point out some details. David Chandler, are you here? Yes.
This is the destruction of the South Tower of the World Trade Center, viewed from a helicopter to the south. This particular video clip is rich in details that call the official story into question. Notice the numerous explosions on the west side of the building above the impact point. As the top 30-floor section falls, it tips to the east. It starts off intact, but then it disintegrates in midair. Gravity alone could not cause the top section to disintegrate. When an object is in free fall, there are no internal stresses. It should have hit the ground in one piece, but it didn't. Some of the debris is clearly being accelerated by forces other than gravity. These effects can be caused by late firing explosives, which can produce a white smoke trail. White smoke, consisting of aluminum oxide, is a byproduct of the thermite reaction. While producing this video, I ran across one rocket projectile I had not seen commented on before. This one stopped midair and changed directions. Even taking perspective effects into account, this projectile lost one component of momentum and gained another. That requires an impulse. Note that the rocket trail does not point back to the building, but the point where the impulse occurred. Let's take it from the top. There's a lot going on. Watch for the smoking guns.
This is outrageous. And when I saw this first time, I said, that could be our red grade chips. Take a look at these fragments. Maybe I should stop here. Why won't it do that?
Forces other than gravity.
Here you see a fragment which is going obviously to the ground faster than free fall. How can anything move towards the ground faster than free fall? If you're standing in a tower and you fire a rocket to the ground, it will sure go faster than free fall. And furthermore, as we proceed...
These effects can be caused by late firing explosives, which can produce a white smoke trail. White smoke, consisting of aluminum oxide, is a...
Look at these trails. And now, up until this point, I thought all the white dust coming out of the towers was crushed wallboard. There was plenty of wallboard, and it's white. But this is not what wallboard would look like if you crush it and throw it out the window. These are rocket trails. And this
byproduct of the thermite reaction. While producing this video, I ran across one rocket projectile I had not seen commented on before. This one stopped midair.
This is crazy. It goes out like this, and then it changes direction 90 degrees. And it still tracks a white smoke trail after it. What are we looking at here? This is rocket fuel. Or rather, I would say, maybe we should reverse our vocabulary, because maybe it's a bit outdated. We have seen all this dust coming out here, white smoke fragments. Is this explosives? Hey, come on. Yeah, and also we see, remember, as Kevin just told us, that the dust coming out is actually toasting the cars. You see, this is not mechanical. This is because, and this car did not burn. You still see the chairs in there. So it was very, very hot and reactive. Is this explosives? Well, yes. Is this rocket fuel propellant? Well, yes. Are these incendiaries? Well, yes. Maybe these terms are obsolete in the age of nanotechnology. In my experience, we are seeing something which is all of it. So we could call it late firing incendiary explosives. And what I would suggest here as a collapse scenario is actually, I may come up with a wild suggestion while they're doing this, but they're removing the external panels by putting nanothermite on the back of it. Now, I'm realizing that I'm maybe a little late, just a little, because now I want to turn to the health aspects of the World Trade Center dust, which we all know that it was not very healthy to be a first responder or a worker during the cleanup operation. And it took actually 3 months at least to put out this fire. I call it the longest smoking gun in history. And to walk around there without breathing protection surely could not be very healthy. And there are numerous accounts of this. The number of responders has been discussed. What I've seen in a medical journal, and the estimate is between 60 to 70,000 of people were exposed to the dust for an extended period of time. And come on, yes. And last year there were published a paper in Experimental Health Perspectives by a group of doctors from the Mount Sinai Medical School in Manhattan, prestigious Sinai, and they looked into the lung tissue of World Trade Center responders, and we should see what they found. The picture to the left here is from a lung tissue, and they found some thread-like tubular structures in 4 out of 7 patients which were ill, in numbers ranging from 11,000 to 230,000 per gram wet tissue. This is the same material which they found also in the World Trade Center dust, which is moving around here somewhere. And this is a sample of carbon nanotubes, which is shown, it's a completely independent sample, which is shown for comparison. So now I'm introducing a new nanotechnology concept, carbon nanotubes. What are they? Well, they are tubes made of carbon, but they are very, very, very small. These pictures taken again from another presentation have this space bar here, I think is 100 nanometers. Maybe this close up is better. Well, I cannot read actually what is here, but they're very, very small. They're made of they can be single-walled carbon nanotubes, and they can be multiple-walled carbon nanotubes. They're very, very strong. They're hundreds of times stronger than spiderweb. They're so strong, they're actually a serious project going out that you can connect the Earth with a space station via a ladder composed of carbon nanotubes. So you can actually climb 300 kilometers out in space and back again, and some kind of vehicle should go up in it. Very, very strong. These are hot items in nanotechnology because they have a whole range of electrical, chemical, and mechanical properties which are very desirable. And we go back to these findings in the nanotubes in the World Trade Center lung tissue. The control group here were 14 construction workers in old cases. The Mount Sinai, they can go back to into their tissue bank and pull out as many patients as they want, diagnosed with asbestos fibrosis, and which meaning these are construction workers which has been exposed to building dust for extended so long time that they actually got too much asbestos, and also 20 healthy non-construction workers. None of them showed the occurrence of carbon nanotubes in the lung tissue. Formation of carbon nanotubes requires 3 conditions must be fulfilled. You must have very high temperatures, and you must have a source of carbon atoms, which means an organic chemical present, and you must have a metal catalyst, among which iron happens to be one of the best besides cobalt. And so this triggered the thought in some of us, well, this means that ignition of the nanothermite should be ideal circumstances for formation of nanotubes. It has taken us some time actually to get together and do this experiment, but Kevin Ryan just showed you in his backyard how he ignited the nanothermite he had produced himself. And he sent it to me a couple of weeks ago, and it is here. So this is the residue from Kevin's together with his kind letter, which I can, just give it to the panelists so they know that. No, let me show it to the audience here. So this is the residue. Kevin, he took. You remember he came in. He took the beaker and you saw down into it. Yes. He left it cooling a little bit. He put it into a letter and sent it to me. It is here. And what I did then is to take a little sample out of this, pouring a few milliliters of alcohol, ethanol, onto it, making a slush in a mortar, actually, letting the particles, all the metal particles, all the heavy particles precipitate. And then you take a little drop of the supernatant liquid, you put them onto a copper grid, which the panelists can also see here, they're very, very small. And you let the ethanol evaporate. You put them into a transmission electron microscope, and this is what you see. And that's it. I made 4 samples. They are all here. This is sample number 1. And you see exactly the same structures here, and there's no other explanation for this. This is again sample 2 here. What you can do, luckily we can do energy dispersive spectroscopy very locally on this sample, taking on this bend here. I know it's hard to see. I haven't had time to do good plots. So let me tell you, what you see here is carbon only, and then you see copper, but this is because they're lying on a copper grid. So this is background, nothing else. Most importantly, we do not see any fluorine, because the plastic that Kevin used for making this preparation contains fluorine, meaning that this is not plastic threads. There's nothing else but carbon in it. This is another sample, very, very dilute sample. This is an overview of the copper grid, actually, because we only applied half a drop onto the copper grid. And the items here are this one. This is a close-up of one of them. Across here is about 1/1000th of a millimeter. These are the dimensions of these chips. This I like in particular, the one here to the left, because, it's not. It's very unstable, I think. I shouldn't have put in a new battery. So this is the perfect dimensions of carbon nanotubes. This is carbon nanotubes. I wouldn't come up with this if I didn't believe what I was saying. This is carbon nanotubes. Again, we're doing energy dispersive spectroscopy. This time we also see aluminum oxide, which is not unexpected. It's probably all over, but we have to look closer into that. But it is definitely not aluminum oxide which is making on these structures. Aluminum oxide cannot do that. Most important is that there is no fluorine, and that is about it. This is a picture from the patients, the Mount Sinai study. This is what we find as a product of the nanothermite reaction. And please remember that none of the control group showed this feature. So if you ask, couldn't the nanotubes come from somewhere else? It's true, it is formed combustion of diesel and in much smaller amount and in oxygen-starved fires. But the control group have been living a normal life, except that they actually caught asbestos fibers. And none of them showed carbon nanotubes in their lungs. The goddess of justice, in my language we call her Justitia. And she is usually depicted, she's blindfolded, she carries a sword and a balance. And the implication of this obviously is that her judgment should not be biased by her own opinions. It should only be based on whatever the hard evidence presented in the case. Now, scientists, we don't use swords in our work, but we can definitely use a balance. And we try to do our best not to make our personal minds influence. We try not to see, actually. The balance should determine the whole thing. So you could say that justice is blind and science is blind, but we are not dumb. Thank you.
Thank you very much, Niels Harrit, for this presentation. Professor Jenkins will begin the panelists' questioning.
Thank you very much. I hope you'll bear with me. I want to go through a rather, what might be described as a plodding set of propositions. My purpose here is to try to get a sense of where you stand on the question of how certain can you be from the tests which you have described to us today, and I guess I should say the whole set of tests, how certain can you be that they lead to the conclusion that someone acting on behalf of the interests of the U.S. government or an agency of the U.S. government placed nanothermitic material on the girders or the columns of the building in order to bring them down? Now, if that's not your chain of reasoning, then just assign it to me, and then you could criticize me.
Of course, I cannot do that.
But
I can say that I have a very hard time imagining that Osama bin Laden could do that.
okay. Well, can we go?
That's all I can say.
All right. Can we go step?
Yes, please.
Can we go step by step through a short series of propositions which I think you have to entertain in order to get to that conclusion? Would you just bear with me for that?
No, I don't. I'm a scientist. I present evidence, and the political. Usually, when I do presentation, I say that it's from the start that political statements are not accepted.
I'm not about to make a political statement. I'm about to propose a series of propositions, the truth value of which I think would warrant, or to some degree, and that's what I want to know, to what degree this conclusion is not I'm not asking for a political judgment.
Okay. Well,
Well, I think the first proposition we need to consider is whether the results of the tests are reliable. In other words, if carried out independently by competent scientists, would they be replicated?
yeah, what should I say?
Well, what's your view? Would they be replicated?
Of course, I believe that.
I think so.
Yeah,
Yes. I mean,
but,
I'm not.
but the nanothermite, if I was asked, is this a standalone forensic proof? And I would say no.
No.
It should be seen in the context. But together with all the other things that we have heard today, the nanothermite, it fits into the picture.
I just want to see what the results of your tests in your thinking warrant. Now, I think the second proposition that we need to consider is, are the tests 100% valid on the presence of the manufactured material that we call nanothermite? Now, there are many diagnostic tests, as you know, for disease, which can produce false positives. But maybe this is not that kind of test. Maybe it's more like DNA matching, which apparently
No.
does not produce false positives.
No, not really. I don't want to carry this too far.
All right.
A scientific paper is a set of data, a discussion, and the best hypothesis. And that's it. And the best hypothesis stands until you come out with a better hypothesis. All I can say is that we published this 2 years ago, and nobody has come out with a better hypothesis. If you call this thermitic paint or you call it painted on thermite, I don't care. We've seen the consequences, and again, you have to see it in the context. The 5.87% of iron spheres found in the dust is a huge amount, as Kevin pointed out. And what maybe we forgot, both of us, is to say that the nanothermite prepared by the salt gel method is very versatile in terms of application. You can spray it on, you can paint it on, and I thought in the beginning, now, why should anybody paint this thing on? Why should anybody spray this thing on? And I said, this is rubbish. Until I saw David Chandler's video. And what he's doing, he's a good teacher. He's just pointing. Look. And you see the fragments coming out. You see the rocket trail afterwards. It's white. What can it be? In science, the truth is only the best explanation of the day. And prior to 1633, the world thought that we thought that the world was the center of the universe. And then Galileo came along, and he got beaten up for saying something else.
But doesn't your electron spectroscopy, isn't that signature, in your view, highly determinative, that it is the signature of something called nanothermite?
Yeah, otherwise I wouldn't stand here. But you're free to think otherwise, obviously.
Well,
I believe
I'm
it.
asking what your view of the certainty of that signature is, that it reveals the presence of nanothermite.
Yeah, it does.
It
Yeah.
does. All right, that's fine.
But science, maybe I'm jumping the gun here. Science is a matter of believing. If you're making an experiment, you're repeating it, but you don't keep on repeating it. And at a certain point, you believe it. You're setting a steel-framed high-rise on fire. You observed it does not collapse. Right. You repeat the experiment, again and again and again. At some point, you say, steel-framed high-rise do not collapse due to fire. That's what you believe when you've seen it a sufficient number of times. Or if you're exposing a thing to gravity, there is a definite chance that this one will go upwards when I release it. It's not zero. But we have seen it so many times, so we believe that it will drop, and it does.
I only have 2 more propositions to go, so...
Please.
The third one is that the source of the nanothermite can only be from explosives attached in some way to the steel columns of the buildings. There is no other possible source. I mean, when we were graduate students, we used to like to talk about Gedanken experiments. I suppose the Gedanken experiment here is, if you could get your hands on many other similar buildings destroyed by some other means, for example, demolition from conventional explosives, they would not yield the positive test results for nanothermite.
Nope.
Or do you believe that?
Now, we have looked into the demolition in Las Vegas, some building, looked into the dust from one and other demolition. There's no nanothermite in there, or any thermitic remains.
Okay. So this is evidence that there was nanothermite material attached at some time to the steel columns of the building.
Well, until today, actually, I have never engaged myself in hypothetical blast scenario. This is the first time I come out and say, well, this might be the red grade chips.
All right, now we're at the last one, so
You're welcome.
I'm not sure I worded this as carefully as I should have, but let me try this. Only someone acting in the interests of the U.S. government or an agency of the U.S. government, such as the CIA, could obtain this nanothermite. It could not be made, bought, or stolen by anyone without the support of the U.S. government.
Well, I don't know.
Okay.
But there
So
are
that
other governments. We know that actually quite well that the French government is working with nanoenergetic materials. I'll bet the Brits are doing it as well, and probably the Russians have been very good at thermite in torpedoes and grenades between the two world wars, etc.
So that's the weakest one. That's the proposition with the least truth value in your view. I mean, you can't, your certainty on this one is less than on the other one.
Yeah, of course. I'm not pointing fingers. I'm opposed to crime, and I think we should have an investigation.
I agree with that, but I'm still asking about this, your degree of certainty, and I take it that this last proposition, that the possession of this material for this purpose would exclusively be possible by someone acting with the support of the U.S. government or an agency of the U.S. government, that proposition you do not find completely convincing or completely certain, let me say. Is that fair?
No, I think it's not.
All right.
Because this, as Kevin Ryan has pointed out, there is a connection between the thermite working national. I'm not an American. I come from a little country across the Atlantic. So maybe I should refrain from asking for answering that. I don't know. Yes.
Thank you. Professor Johnson.
Yes. I'd like to ask a question about chemistry. We've heard a lot about the element sulfur being a component of nanothermite, but in your BSE images, we did not see very much evidence of sulfur.
That's right.
Is an
That's right.
explanation?
That's right. The red grade chips and the nanothermite cannot account for the sulfidation of steel. Where is Jonathan Cole? Oh, there. So what we have actually, there must be at least two kinds of thermitic material there. The red grade chips and the thermate, which did the sulfidication of steel. What I think is that the core columns, the hard work, was done by thermate. Why, whatever is happening to the perimeter columns, where you see the panels actually being rocket propelled through the air, I don't know why. I have a suggestion. It's wild, but I think that the hard work was done by the thermate to the core columns, and explosives were also doing a lot of hard work, throwing things up and out, and nanothermite was a third thing.
A quick follow-up question. It's unlikely that the nuclear explosions were involved, but it was suggested yesterday or the day before that there was something called non-ionizing nuclear weapons. Is there such a thing as a nuclear blast that would not produce radiation?
I'm not a nuclear physicist, but if you ask me, if we go out in the corridor, I would say this is complete nonsense.
I think I agree.
Professor Lee.
Well, you definitely took us on a wild ride through the very microscopic details about this nanothermite. But once again, you hesitate to, well, more so than in the past, but you're bringing us to the doorstep and saying, now it's your call if you want to walk through that
That's
doorstep.
right. That's right.
So I'm going to ask a really picky question. In the original discovery of nanothermite, you put up the formula, and I believe Kevin put up the formula for nanothermite, the original one from 1893. And there's this tiny detail difference between what you put up and what Kevin put up. There was 848 kilojoules in one formulation and 853 in the other formulation. And is this just part of the noise in the system, or is there any significance to it?
Well, I didn't recognize they're both huge numbers.
Okay. But I'm curious, you know.
Maybe he looked into another book than I did.
Yours was
Yeah, that's right.
848 and his was 853.
He's the professor of chemistry, so it was right.
Okay.
It was the kilojoules. Was it
Kilojoules, yeah.
And what was the unit?
Kilojoules.
Okay.
KJ.
Well, Kevin and I will resolve this afterwards
Okay.
over a beer. But they're both a lot. I mean, they're very energetic. There's a lot of heat being developed. And some thermites, some thermitic reactions with molybdenum trioxide can reach 4,000 degrees centigrade. Lawrence Livermore Laboratory in 1993, they made a thermitic point charge going through 4.3 meters of steel. Zip. 20 years ago.
A question from Judge Imposimato.
Yes, thank you. The dramatic problem is that often the judge is not able to control the validity of the evidence of nanothermite science and must trust the expert. Anyway, where the aluminium and the iron oxide in the metal particles part the tower structure since its construction, or have they been put into the tower, the building later? If so, for what reason? How could this be done without the people working in the Twin Towers noticing? How this observation been presented to any government authorities?
Yeah, basically this question: how could get all these incendiaries and explosives into the building without being noticed? Well, I've used on pallets is my standard answer. If you want to bring these amounts into the buildings, I would put them on pallets and then drive them in. But you have to be on good terms, of course, with the security, and you should not put a sign on these are explosives for demolition. So it's all. Kevin Ryan has written a series of papers called "Access to the Towers." So it's only a matter of say good connections, and this has been studied. Also, which has been presented previously, the key, at least to the Twin Towers, are the elevator shafts. And I have spoken with the Dane actually, whose daughter was working in. There was a permanent fire station actually in the towers, and she was a volunteer there, and he lost her. But he has been employed by the Port Authority, and he had been into the Twin Towers, they say the hidden Twin Towers. You can move around in the towers without ever getting out into the office space. Once you're in there, there's a whole world around the steel beams where you can move around without getting out in any corridors in it. And the key access is the elevator shafts. So once you're in there, you are in. If you get past the janitor. Yeah.
Yes, Professor Lee.
One line of inquiry that we haven't pursued but might be worth pursuing, and I guess this is addressed to both Dr. Harrit and to Kevin Ryan, is when Timothy McVeigh, for example, was building his putative alleged bomb out of fertilizer, there was some record of where the fertilizer, large quantities of fertilizer, was bought. So I'd be curious to know if there are registries or inventories in the United States of thermite. And so, gee, isn't it curious that so-and-so, some obscure person, just ordered 20,000 pounds of this stuff? Isn't that kind of curious? And would this be conceivably a line of inquiry to pursue?
No, it is not. It is not in the chemical catalogs. It is. This is military stuff.
Military
Yeah,
stuff.
we're guessing. We're guessing a long way, but they have to do presentations at symposium once in a while. So these are conference proceedings we are citing and internal reports. But be sure that once they write it in a report, it is insignificant. What Kevin has prepared is not the same stuff in the red grade chips. We don't know what the polymer in the red grade chips is. The published recipes, which Kevin has been applying, is not exactly the same thing.
I'm actually on a different tack. And that is when the anthrax scare came out, it quickly emerged that there was only, was it 1 lab or 4 labs in the world that could produce the weaponized anthrax.
Yeah.
And so that quickly narrowed down the scope of the investigation, even though we still don't know what the final outcome is. So applying a parallel thinking, could we say where in the world is this stuff being produced, and who's producing it, and where is the Pentagon contract number 34795, which requisitioned this large amount?
Well, I suggest we leave this for the grand jury. Yes.
Professor Johnson.
Yes. We suffered some 3,000 deaths in the event, but you say that 60,000 to 70,000 people have been exposed to the dust, and that the dust is clearly toxic. I wonder, the nanotubes that you identified, are these carcinogenic? Do we know?
You were actually, I'm glad you asked this, because the health effects of carbon nanotubes, is a new material, and I've asked Adnan did you print out? No, not yet, but I can provide a review from 2006, which is describing the health effects of carbon nanotubes, and I can get it here on the screen and come up with all the medical expressions. Directly carcinogenesis, I think, has not been demonstrated, but they've been feeding mice and rats with this stuff, and it is not healthy. It is much the same effect as asbestos. But if I'm just a chemical account, the nanotubes are hydrophobic, meaning that they are trying to get out of the water, while asbestos are hydrophilic, they want to stay in the water. So my guess is that the nanotubes, they slip into the membranes of cells. So it remains, I hope that this finding will cause further study, of course, into the lung tissue of the first responders, because they're very ill. I will not draw any specific connections to any form of cancer here. But I'll provide this paper I'm talking about. Hopefully it will be available later on to the panel. You'll get a review of health effects of nanotubes.
Are there further questions? Let us thank Professor Harrit for that remarkable presentation.
Thank you. Thank you very much.